Welcome to the Explainer. Today we're tackling a phantom menace hiding in literally every hospital and clinic. Imagine taking a perfectly aimed photograph, but right as the flash goes off, invisible beams bounce all around the room, totally fogging up your picture and actually zapping the photographer. Well, in radiography, this is exactly what happens. It's called scatter radiation, and it's the ultimate villain. It ruins medical x-rays and poses a very real, invisible hazard to the technicians taking them.
Here's our roadmap for today. We're going to define the scatter radiation problem, look at filtering out soft X-rays, restricting the primary beam, unlocking the power of grids, and finally, using the air gap technique. Let's get right into it.
Section 1. The scatter radiation problem. So what exactly is scatter radiation? Well, it happens when the primary X-ray beam hits a medium, like say a patient, and completely deviates in both its direction and its wavelength. If it scatters at an angle less than 90 degrees from that primary beam, we call it forward scatter. If it bounces back at more than 90 degrees, that's backscatter. The big takeaway here is that scatter is basically rogue energy. It bounces right off the patient, gives us absolutely zero diagnostic value for the medical image, and instead just becomes this invisible hazard to the radiology workers in the room. To really grasp the visual fog problem we're dealing with, think about an open beam versus a collimated beam. An open beam irradiates way more tissue than necessary. All those scattered photons bounce around and create massive image degradation, literally throwing a gray fog over the anatomical details you're trying to see. But if you tightly control or collimate that beam, less tissue irradiated means less scatter, which ultimately gives us a much, much crisper image.
Moving on to Section 2, filtering out soft X-rays.
We can actually sift the X-ray beam by putting physical barriers right between the tube and the patient. There are two main ways we do this. First is inherent filtration. This is stuff built straight into the machine itself, like the glass envelope, the insulating oil, and the backlight window. Then we have added filtration, which uses materials like aluminum and copper. Why do we need these? Well, they're designed to yank the less energetic, soft X-rays right out of the primary beam. Because, honestly, those soft X-rays don't even have the juice to pass through the patient and hit the film anyway. Without these filters, they just get absorbed by the body, needlessly bumping up the patient's radiation dose. And nobody wants that.
All right, Section 3, restricting the primary beam.
So we can restrict the beam using devices called beam collimators. By intentionally regulating the beam size to strictly match only the part of the patient we're examining, we score a massive win-win. It heavily reduces that rogue scatter radiation, significantly improves our image quality, and, most importantly, it decreases the patient's dose simply by shrinking the exposed area. Better pictures and better patient safety. It's absolutely crucial.
Now, mechanically speaking, the simplest way to do this is with an aperture diaphragm. It's essentially just a flat sheet of lead with a hole punched right in the center. Could be circular, square, rectangular, but there's a catch. Because of how radiation travels, the edges of that hole create a pretty large, blurry edge shadow on the image, known as a penumbra. Plus, it's kind of a huge hassle. You literally have to swap out a different size lead sheet for every different size of film you use. Which naturally makes us wonder, isn't there a better way to restrict the beam, ditch the constant swapping of lead sheets, and get rid of that blurry penumbra edge? Since the basic lead hole wasn't really cutting it, mechanical ingenuity had to step up to the plate.
Early on, engineers came up with conical or cylindrical metal tubes with lead bases to literally channel the X-ray beam. And sure, they do effectively restrict the beam to a specific field size, but honestly, they're still kind of bad at totally wiping out that blurry penumbra. Cylinders do a slightly better job than cones because the final collimation happens further away at the far end of the tube. Still, you're stuck with fixed sizes, so they're only really good for very specific exams.
Enter the modern gold standard, the variable aperture collimator. Instead of a fixed hole or some static tube, this brilliant device uses adjustable lead shutters. You can slide these shutters around to perfectly frame the exposure field into an infinite variety of rectangular shapes. It even shines a light onto the patient so the tech can visualize exactly where the X-rays are going to hit. This drastically cuts down that blurry penumbra and guarantees we're only exposing the precise area we need to see. Which brings us to Section 4, the power of grids. Here's the thing. When you're imaging a body part thicker than 10 centimeters, scatter becomes a massive headache. To fix this, we use a grid. Think of it as a flat plate made of alternating strips. You've got radiolucent interspaces made of plastic or aluminum and radiopaque lead strips. We slide this grid directly between the patient and the film cassette. The straight-shooting primary beam passes right through the clear interspaces, but that rogue scatter radiation, it flies in at wild angles, slams right into the lead strips, and gets safely absorbed. To measure just how good a grid is at its job, we use something called the grid ratio. The math is super straightforward. It's simply the height of the lead strips divided by the distance between them. A higher ratio means those lead strips are either taller or packed closer together, and that means a much stronger ability to soak up high-energy scatter radiation, which is especially crucial when you're working with higher voltage X-rays.
Now, grids have several technical characteristics, but the absolute most critical trade-off lies in the Bucky factor. The Bucky factor measures the total quantity of radiation the grid absorbs, and this reveals a really tough compromise in radiology. See, while higher ratio grids do an amazing job of clearing up image contrast by eating that scatter, they inevitably absorb a big chunk of the primary X-rays too. Because of this loss, you actually have to crank up the exposure factors to compensate, meaning, unfortunately, more total radiation exposure for the patient.
And that brings up a really fascinating mechanical dilemma. The grid is literally packed with solid lead strips blocking radiation. So wait, can a grid hide its own shadow? A huge problem with static grids is that those alternating lead strips can actually show up as faint white lines on your final X-ray image, totally obscuring the tiny anatomical details the doctor is trying to diagnose. So how on earth do we fix that?
The answer is absolutely genius. It's called the Potter-Bucky diaphragm, or just the moving grid. This device mechanically shifts the focused grid right underneath the X-ray table at a perfectly uniform speed, exactly during the split second of the exposure. By moving the lead strips while the shutter is open, the machine literally blurs the grid's own structural lines completely out of existence. The scatter gets blocked, but the grid lines just magically vanish from the final film. Finally, let's look at Section 5, the air gap technique. Sometimes the simplest solutions are the best. The air gap technique relies purely on physical distance. By intentionally putting more space between the patient and the film, we give those divergent, scattered X-rays room to travel away. Since scatter shoots off at angles, if you just move the film plate back far enough, those rogue X-rays will completely miss the plate altogether. Only the straight primary beam registers the image. No heavy lead grids required, just open air. As we wrap up this explainer, I want to leave you with a pretty provocative thought. We've seen that improving image clarity with heavy-duty tools like grids inherently removes some of the primary beam, right? And that often forces us to actually increase the overall radiation output to compensate. So how do we perfectly balance a crisp, readable medical image with ultimate patient safety? It's this constant, incredibly precise balancing act happening between physics and medicine every single time you step into an X-ray room. It's not just snapping a picture. It's a carefully orchestrated dance of taming the invisible. Thanks for hanging out with me for this explainer, and keep looking for the structure behind the science.